Hello everyone. So in the series of software defined radios and its practical applications, we were discussing the digital predistortion techniques, and in this lecture we will cover the linear and nonlinear, both the techniques, the algorithms and the results with the practical system. So as we were discussing in the last lecture, we have to select one of the topology, and once we have selected the topology with which we want to go for the modeling, then second concern is the selection of algorithms. So there are several filtering algorithms in the literature, but first of all we have to see how we can apply those algorithms. For example, in linear filter theory, we have some of the examples where we do the fitting, and in our Wiener-Hammerstein model we are using FIR. So we will start our discussion from the FIR filter, their fitting, and then we will take the nonlinear to linear mapping for the memory polynomial model, and we will show how we can apply those in the nonlinear terms. So for FIR model, our yn was a function of input signal and its previous values of the input signal. M is memory depth here, so basically we can represent the same thing as a matrix also. So if we take different value of n from n equal to 0 to not 0, it will have integer value, positive integer value 1 to up to n, then we can basically represent this as y1, y2, y3 up to yn output, and xn can be represented as x1, x0, x minus 1 and so on till mth value. And coefficients can lie here. Let's put it am. So it will be am here, which will be with respect to this one. Similarly, it will have all the values till x capital N, and this value will be x n minus m plus 1. So by arranging these values, it will be x2 value, then x is previous value, its more previous value, x minus 1 and so on. So we can arrange this term as this one also. So we can represent this as y, this as x, and this one as a. So a will be representing the coefficient matrix, this x will be observation matrix, which is including all the input data. Actually this matrix, coefficient matrix can also be called coefficient vector, it is simply a vector, and this will be the output vector, output signal vector. Right. So if we are able to represent in this way, then easily by using matrix calculations we can calculate our coefficients here. So what will be coefficient here? It will be x inverse y. Now if this matrix x is not square, and if it may be singular, then that inversion it is not possible. So we have pseudo inverse techniques which takes care of inversion process even if this is not square, even if it is a rectangular kind of matrix. So normally we go with the pseudo inverse techniques such as Penrose-Moray inversion technique. So this is the basic arrangement of the data here. So, observation matrix, output vector and the coefficient vector will be there. Now, it was for the FIR filter which we use in the Viram-Hammerstein. How we will calculate our coefficients in the nonlinear filter. So, for the neural networks it is entirely different kind of processing, they use step by step techniques, but for the memory polynomial voltage series when you are using polynomial we can do nonlinear to linear projection. Technique. What is this technique? Basically, here if you look at this, it is a linear algebraic condition which we are imposing here and we are solving for that one. When we are talking about nonlinear terms, if we can do the projection so that nonlinear terms can be represented as a linear term, then we can still use this equation. And how can we do so? For example, if our function is y is equal to a1 x square, we know that is a nonlinear equation, but if we select x square to be some other function, let us say x1, then with respect to x1 and y it is a linear equation. So, by choosing x square equal to x1 we can still calculate a1 using linear techniques, and this is what we call a nonlinear projection. So, this is what we can easily use for the nonlinear memory polynomial. For example, memory polynomial equation is given as summation over j from 0 to n minus 1, k minus 1, because k we are using for the nonlinearity order, and m from 0 to m, which is m is the memory depth which we have discussed in the last lecture. And this was the equation for the memory polynomial. Now, how we can we do this projection which I was talking about? Now, instead of this equation we have to map this equation. So, in this equation also we have some coefficients which are dependent on m and j, and this coefficient we have to find using this kind of techniques. So, can we arrange this in terms of matrix and can we apply the linear techniques? This is what we have to see. So, y again we can arrange from 0 to n for the n number of data, and after that observation matrix has to come into picture. So, the observation matrix will contain x1, x1 absolute of x1 and so on for m equal to 0. Right. So, let us make this big so that we can understand all these terms together. So, for m equal to 0 we have done the calculation till here, x1 absolute value of x1 to the power n, not n, we are taking it to be k. K is our nonlinearity order, right, for m equal to 0. After that, in the next column we start taking values for m minus 1. So, m equal to 0 is this one, and then we take m equal to 1 terms, means previous values. So, x0 and absolute value of x0 until m we can keep doing this. For example, we have done this for m equal to 0, then we had done for m equal to 1, then m equal to 2, and then finally for m equal to capital M, right. So, it will be what? 1 minus m, x1 minus m absolute of x 1 minus m, next will be squared, and last term will be x 1 minus m to the power k, and this will be its observation matrix. Now next term x2, and the same thing x2 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 will be here. Here will be x1 and x1 and it will be x2 minus m, and so on. So here what we have done, our nonlinear kernel we have represented in one column. So now we can again apply our linear equation. So after we have defined our observation matrix, it is our y. This is, let's remove this equation now, which is the equation for memory polynomial. If this is whole equation is our x, which is the observation matrix, and as you can see, if I multiply this whole equation with a new vector, so let's make some space here. Okay, let's suppose this matrix finished here, and this is to the power k. Then we can again multiply our a m k, right. So we can define our coefficients here according to all the values of m's as well as k, and when we multiply we get our y output. So basically again we can represent our equation in a linear fashion, and if we solve this function, because we have done the projection, we have put the nonlinear terms in one element of this matrix, we have done the mapping of nonlinear to linear. So we can easily calculate our a again using the inversion of this matrix by using pseudo inverse methods. So this is the way we can arrange our matrix, and once we know this relation, then there are different type of algorithms which we can select to make it more easier there. So there can be two types of processing. One is batch mode. This example which I was showing you here, what was for the batch mode, because you are using from data from 1 to n and sample at one time for making matrix. But sometimes there are applications when the system is changing very fast. In that case you want to do sample by sample data sampling. It means you will be using only first element of this and first vector of this and only this one. So we are not using batch mode anymore, and it is sample to sample adjustment of the data. So y is being processed only for single data at a time with total number of coefficient. In both the cases you will notice that number of coefficients are same. In one case we are using complete matrix to include n data, in one case we are processing one data at a time. So based on our applications, whether our system is changing fast or do we want fast convergence, then we can choose our batch mode or sample to sample processing. So in the batch mode processing, we have basically least square methods and recursive least square method. So what is a least square method? Basically that you arrange your output matrix, you use your observation matrix, and you define your coefficients, and based on this batch mode you can apply your least square method. So by using pseudo inverse of this x, you are able to get your coefficients. So it is one step process, because once you have defined your y and x observation matrix in one step for n data, you will have single solution. Now least square method, because you are using block based processing and you need to do the pseudo inverse, it will take more resources in digital computation, because doing the inversion of the any system, it is a difficult thing and resource consuming thing. So because of that there are many methods where they try to reduce the complexity of this kind of method, and those kind of method try to make this pseudo inverse more efficient. So, it is least squares method. Using pseudo inverse. So, in this case your A becomes so for calculating this portion, which is the pseudo inverse, if you see, if I wanted to do x inverse y, it will be inverse of that one. Instead of using that, we are using this quantity which we used in the least square method. There are methods such as singular vector decomposition, etc., where we try to minimize the complexity of this portion. So, this is entirely different research area, so we are not going deep into it, but we just want to maintain that this is the one step method and it converges very fast. In sample to sample processing, you have gradient descent method and the mean square algorithms. Quickly going through those methods for the overview. GD method, steepest gradient method, these are the names of this method, and this method we update our coefficients given by this equation. Where this Gn is actually gradient of this cost factor with respect to weights, and this cost factor is actually MSE, mean square error of the output. So, you get your estimated output, you get the mean square error, J is equal to 1 upon n yn minus y estimated whole square. You define this and then you see its variation with respect to W by differentiating it, and in the real life, if it not differentiation, you take the difference with respect to the previous step and you apply this formula, and the coefficients can be adjusted by using the previous quotient value and the new gradient value. Again, you can see it is a sample to sample processing method, because you are taking one n at a time. You are not taking n equal to 0 to n, from 1 to capital N in one shot. Instead of that, you are sampling, taking 1 and then you are processing, updating your quotient value, and then you are taking second and you are updating and processing these values. So, for stochastic method, where there is noise in the system and you are using variance and mean, those kind of system, it was proposed basically to simplify for the deterministic signal like we are using right now, where we have the signal in our hand and we want to work on the based on that data. Least mean square method can be used. The statement of this one is so it is un, let us make it xn because we are calling input signal as xn. So, again it is sample to sample processing, you need the conjugate of en, which is the error, yn minus y estimated, and the conjugate of that one, the original input data, and that this is the step function in the both of these. We can select it by ourselves to see the convergence performance, and we keep tuning our W to get our best performance till this y minus yn becomes minimum. All these methods, they are trying to minimize this mean square error. So, basically if it is number of iterations So, because it is mean square error, if we draw this with respect to W, for a particular value of W, you should be able to get this minimum value of J min. So, in least square they try to get in one step somewhere near here, and gradient descent and LMS method they try to come here slowly, stepwise. So, this is what we are getting here. Iteration wise least square is one global solution. So, whatever you will get in one step, let us say with iteration you will have 0, 1, in one iteration you will have your least square solution. For gradient descent and the LMS, they will be reaching here slowly. So, if I say LMS and gradient descent, somewhere here they will be working like this with many iterations. So, we can see here the processing here is very much simpler, just the multiplication of two terms and the addition, and here little bit complex with respect to this one, because you have to calculate the gradient. The benefit here is that gradient descent method can actually reach near to this point, but in LMS, because we are removing the gradient value, the stochastic properties coming back into picture, because of that it just keep rotating here and here in LMS method. In least square method it is trying to reach here in one step. So, these methods are simpler to implement, less computation. Least square method you have to do the inversion, you have to deal with the matrix. So, of course, that is more complex method. So, while keeping this in mind, recursive least square is a compromise between these two. So, if least square is getting here and LMS and GD are just reaching here, RLS is giving you convergence somewhere in between. Okay, so, if it is LS, it is GD and LMS, then in between it will be RLS, and again it is a compromise in terms of complexity also. So, quickly if you look at the equations, instead of using simply one weight update, coefficient update equation, we have set of 3-4 equations, but we are not using inversion here. It is simply the multiplication and division of the terms. So, in this kind of system we define our vector p by ourselves, we choose some p, and based on that p we define our kn, un is our input signal here. Once we get our k value, we calculate our alpha n value, which is basically the error. If you see here, desired value minus input signal into weight vector, so just the error. So, this k and error is multiplied with the previous value of kn, and it looks very much like this method then, apart from the fact that we have to calculate kn and pn here. So, complexity is lesser than the least square method, but higher than gradient descent and LMS method, and convergence speed is faster than these two. So, it is compromised between LS and LMS techniques for this one. There are several methods in the algorithm wise which you can basically, if you go through the Simon-Haykins adaptive filter theory from the Pearson education in India, this version is available in India. Then many details on these algorithms you can perceive from there, but basically once you select the topology, this kind of algorithms you can select easily. So, you have selected the algorithm, let us say we have selected least square method, and we have decided we will go with this method and we will select our topology based on this method. So, for memory polynomial model, we have to select memory depth and we have to select nonlinearity order. So, how do we do that? We keep changing the nonlinearity order from 0 to some value, let us say 20th, and we also keep increasing number of memory depth, and we plot them together, or we just observe them, and whenever it is converging, so it is a hit and trial method. In this case, we can see that if we keep increasing number of memory order, nonlinearity order for m equal to 0, then our system response model performance in terms of ACEPR. We have defined ACPR earlier, adjacent channel error power ratio, which is for the out of band modeling error. It is converging at 9th order. So, k equal to 9 should be able to give us good order. Now, if we use m equal to 0 or if we use m equal to 3, we can see there is a difference of 2-3 dB when we use only m equal to 0 and when we use m equal to 3. So, m equal to 3 and k equal to 9 is giving us good convergence. So, we can choose this value as our model topology. So, m equal to 3 and k equal to 9. The same trend we can see for in terms of an MSE also. We are plotting an MSE for m equal to 0, which is this one, and m equal to 3, which is this one, and we can see that it is also converging at n equal to 9, and again m equal to 3 is giving much better than m equal to 0. So, we keep changing from equal to 0 to 1 to 3, and similarly from 0 to any value of nullity order. When it is starts to saturate or become even worse, then we will stop at that point, because if we keep increasing here we will get the same performance, but our complexity is increasing, right, because we are increasing number of multiplications and additions. So, it is better to stop at this point. So, this way we can choose our topology, and then by chosen topology and algorithm we can apply our model. So, here for a practical system Dorothy power amplifier, we are showing the actual PA characteristic. So, in the left hand side figure we can see that our AMAM is given by this red curve, which is the gain, and it is normalized gain. So, it is around 0. We have removed the small signal gain so that we can just see its performance. Similarly, phase difference, which is AM/PM, it is again around 0. It is shown by black, and we can see it is very nonlinear system. So, by doing the inverse modeling, means by using input as a output and output divided by small signal gain as an input, as we discussed in the last lecture, we again do the modeling using neural network, and I am showing the modeling results here in the right hand panel, and you can see that gain curve is this one, which we received from the model, and the phase term is this one, which also we received from the model. And if we even by our own eyes we can see that nonlinearity profile is inverse of what was for the power amplifier. So, we have a hope that it should be able to correct for the PA nonlinearity here. So, this is what we will see here. In this case, when there is no DPD, no distortion was there, this black curve is showing power amplifier output, and we can see that out of band distortion is here. It was the original signal, 3 carrier signal which has one missing carrier and third carrier. If 3 carriers are on for this WCDMA signal, we can see this is the profile and this is the out of band distortion which is appearing because of the power amplifier. Again we can see when we apply our DPD, then for memoryless model, when we are using m equal to 0, in both the cases this red one is the result of the DPD. So, inverse model is working very perfectly, there is a reduction there, but if we increase m equal to 1, 2 and 3, we can see that it is even becoming better and better, more reduction in the out of band distortion is happening in both the cases. So, this was an example with the LD-MOS class AB amplifier, and it was using the signal with the 10 dB PAPR. Now, we can go to the effect of IQ imbalances. We had seen the effect of power amplifier nonlinearity and how we can use DPD to compromise on that one. Now, apart from the power amplifier nonlinearity, we have discussed IQ imbalance earlier, and because of that IQ imbalance, we also see some extra additional distortion, such as in the constellation diagram there is a tilting of the phase and the distortion which is more than the original signal constellation at the signal constellation point. So, we want to reduce this effect also. We have discussed the image appearing because of the IQ imbalance, and this is what is appearing here. We can remove this effect also using digital predistortion, and in the next class we will be discussing this effect and how we can reduce this by using our digital predistortion techniques. Thank you.